All right, attention please. Thank you for coming today. Today's What Physicists Do is a talk by Dr. Norbert Werner, who's an astrophysicist at the Kavli Institute for Particle Astrophysics and Cosmology at Stanford University. He also works on the Astro-H satellite, which is a joint U.S.-Japanese X-ray astronomy satellite. That will launch next year. Yeah, so that's exciting. He is from Slovakia, and his undergraduate degree is from Košice University in Košice. Just trying there. And he's completed his PhD at the Netherlands Institute for Space Research. He's been in California for 7 years, and I asked him about it, and it's like that's long enough to kind of get the bug to very much like Northern California. So that's his where he is right now. He's going to be talking about the fascinating connection between galaxies and their supermassive black holes, and I don't want to give too much more away. Let's give a warm welcome to Dr. Werner.
Thank you very much for the introduction. So I'm here today to tell you about my research on the largest objects in the universe, which are giant elliptical galaxies, groups and clusters of galaxies, and about how the central supermassive black holes in these systems, their beating hearts, control their growth and evolution, essentially sculpting these systems, making them look the way they do. So most of you already probably heard that the matter is distributed across the universe in a web-like structure. The skeleton of this cosmic web is made of dark matter, and the ordinary so-called baryonic matter then follows this dark matter distribution. You can see it on this image snapshot from a numerical simulation, where you can see that these galaxies here are following this dark matter filament just like pearls on a string. So our so-called standard cosmological model, concordance cosmology, which we tend to call the lambda CDM model, lambda cold dark matter model, is the model which assumes that most of the universe is made of dark energy and dark matter. This model is describing pretty well the dark matter distribution across the universe. However, the evolution of the ordinary baryonic matter is still not well understood. It's very complicated. And it turns out that most of this baryonic matter is not in stars, it's in a diffuse gas. Only about 10% of the ordinary matter turned into stars. The rest is in a diffuse intergalactic medium. Now, why is that? The physics of this intergalactic medium is determined by processes such as large-scale shocks and gas flows that occur during the structure formation process. Then energy and momentum input from jets that emanate from the supermassive black holes in the centers of galaxies. Energy and momentum input from exploding supernovae, which also enrich this intergalactic gas with metals, with other elements than hydrogen and helium. And then by galactic winds that are driven by the combined energy of many, many exploding supernovae and accreting supermassive black holes. Now, how does the energy from all these processes couple with this diffuse gas is not well understood. It's not well understood because this intergalactic medium, I just said it's gas, but it's actually not gas, it's plasma. It's weakly magnetized plasma, which means that the microphysical properties of this intergalactic medium, such as its conductivity, how it conducts heat, or its viscosity, whether it is like honey or like water, this cannot be determined just based on first principles. We need observational constraints to determine what is the conductivity and viscosity of this gas. So to understand how these jets and exploding supernovae actually interact with this intergalactic medium, preventing it from forming stars. So this intergalactic medium is best observed in clusters of galaxies. What you see here is a composite X-ray optical image. Here you can see the individual galaxies from as seen by an optical telescope, and then this pinkish hue, this is an image from the Chandra satellite. It shows the intergalactic medium in this galaxy cluster. It turns out that if you would compare a galaxy cluster to a cupcake, then the galaxies are just the cherry on the top of the cupcake. The frosting is like this intergalactic medium that I'm observing with the Chandra satellite, and the rest, 86%, is dark matter that holds this galaxy cluster together. So let's come back to this image. And what I will be talking about here in my talk today mostly is this frosting, is the intergalactic medium that I observe with the Chandra satellite. This intergalactic medium has a very, very low density. It's 10 to the minus 1 to 10 to the minus 5 per cubic centimeter, and very high temperature, 5 to 100 million Kelvin. It emits X-rays via Bremsstrahlung emission. When you have the ions and electrons, when they fly by each other, they break, they change their trajectory. As they do, they emit an X-ray photon. So most of this emission is due to this so-called Bremsstrahlung emission, interaction of ions and electrons. This gas is in a collisional ionization equilibrium. It means it's not ionized by the light from the stars, but it's ionized by collisions. And the collisional excitation and recombination rates are in equilibrium in this gas. So it's actually very, very simple system, and it's optically thin. So every photon that is emitted anywhere in this galaxy cluster will just escape out. You don't have to take into account when any radiative transfer processes in these atmospheres of galaxy clusters. It's a very simple system. Also, electrons and ions have the same energy or same temperature. There is a temperature equilibrium. And because it's such a simple physical system, when we look at an X-ray spectrum, based on the shape of this spectrum, we can determine exactly what is the temperature of this gas. If you assume some kind of geometry for the emitting volume, you can determine what is the density of the gas. And when you know what is the temperature and density, you can calculate the pressure, the entropy. And based on the spectral lines, we can determine what are the chemical abundances, what is the chemical composition of this gas. So X-ray spectroscopy of this intergalactic medium is a very, very powerful tool. Now, I will start my talk talking about the centers of these objects. Now, when you look at this picture, you can see that at the center of this galaxy cluster is a huge galaxy. And also that there is lots of this pinkish hue, which means that the intergalactic medium there is relatively dense. Because it is dense, there are many interactions between the ions and electrons, which means lots of X-ray photons are emitted. And because they leave the system, they take away energy. As they take away the energy, the gas cools in the center of the galaxy cluster. Now, as this gas cools, one would assume it will form over time large interstellar clouds, which will then cool further, and then they will form stars. So if you actually calculate how much energy is emitted from the centers of galaxy clusters, you get that this cooling rate should be really huge, should be like hundreds of solar masses per year, even 1,000 solar masses per year. So then what you would expect is that these galaxies in the centers of these galaxy clusters should be huge, and they should form stars at a very, very large rate. So they should be blue and filamentary. They should look like fireworks, forming hundreds of stars every year. These should be the most beautiful galaxies in the universe. But instead, they look like these galaxies. Boring. Spheres, red and dead, as we say. It turns out that these galaxies stopped forming stars 10 billion years ago. In the past 10 billion years, they formed only stars at a very, very small rate, like 0.1 solar masses per year instead of the hundreds or thousands. So what's going on here? What prevents the intergalactic medium around these galaxies from cooling and forming stars? The answer, we believe, lies in the centers of these systems. This is a jet emanating from the center of the galaxy M87. Now, I was told that among you are also some amateur astronomers who like to observe with telescopes. So I challenge you to take a picture of the jet in M87. With a good amateur telescope, you should be able to do that. Yes?
Would it need to be in the X-ray spectrum
So,
to capture the jet?
yes, so this jet emits over all the spectral bands, from radio all the way to the gamma rays. So this is now an optical image, but the jets are actually best seen in radio. This is an image from VLA. Here you don't see the stars in the galaxy, which will be all around here. You only see the radio jet. And you see that it is 4,500 light years long, very well collimated, very narrow. Here it interacts with the surrounding intergalactic medium, and then here the jet stops. It's huge, very well collimated, and it's made of relativistic particles and magnetic fields. As these relativistic particles, which means particles that move very close to the speed of light, relativistic electrons, as these electrons then interact with the magnetic fields, they emit this radio emission, and the emission across all the wavelengths. You only see one jet because this jet is pointed very close towards us. It's pointed at us. So actually there is relativistic boosting. You see it much, much brighter. In the same time, there is a relativistic dimming for the counter jet, so we cannot see it. It is there, we just don't see it. But you see here another lobe where it already slowed down, so you know that there is another jet. Now, if you think that this jet is extreme, then look at this one. It's 300,000 light years from one end to the other. The galaxy will be somewhere here in the center. You again don't see it. All you see here is the radio emission from the jets emanating from the center of this galaxy. And here the jets are interacting with the surrounding intergalactic medium. 300,000 light years. That means that you could fit 3 Milky Way galaxies here next to each other. That's how big these jets can be.
Is this SMA?
Yeah. No, Cygnus A.
No, Cygnus A.
So how do these jets come by? Simple picture is that as the matter is falling towards the central supermassive black hole, it forms a disk, accretion disk, from which then two opposing jets are emanated, which then inflate these bubbles in the surrounding intergalactic medium. I will show it again because this is kind of important. The matter is falling onto the supermassive black hole. It forms an accretion disk. From this disk, two jets are launched, and these jets then blow these bubbles, and they drive shocks, blast waves, into the surrounding medium, heating it. So we can see this in many clusters of galaxies. These are all composite images. Let's just look at, for example, this one. Here you can see in the optical image the galaxies. In blue you can see the X-ray emitting gas, and then in this red you can see the lobes, the relativistic plasma from the jets emitting radio emission. And you can see that where the radio emission is strong, the X-ray emission is weak, because these jets, they blew bubbles into this intergalactic medium, they pushed it out, filled it by this relativistic plasma. So when you look in X-rays, then you see there a hole, because X-ray emitting gas is missing in those places. So this is my cartoon model of what's going on here. So what happens here, and this is the theory that this is the process that stops the star formation, that stops the gas from cooling, is that the jets from the central galaxy, from the black hole, they inflate these bubbles of relativistic plasma. These bubbles are initially inflated supersonically, faster than the speed of sound in the given environment. So then they drive shock waves into the surrounding gas. And these shock waves, they then heat the gas. These are weak shocks with very low Mach numbers, only mildly supersonic, 1.2, 1.3, maybe 2. They are not more supersonic than that. Then, as the expansion of these bubbles slows down, they detach from the jet, and then they start rising buoyantly in the atmosphere of the galaxy cluster. Just like water in a boiling water, just like bubbles in the boiling water, or like water balloons. It starts to rise buoyantly in the atmosphere of the galaxy cluster. And as it is rising, it drives turbulence in the surrounding medium. And this turbulence then over time dissipates into heating this intergalactic gas. Now, how exactly does it happen depends on these microphysical properties that I told you about, such as viscosity of the gas, which we don't know. And also, as these bubbles are rising, in their wakes, they drag out from the center of the galaxy the lowest entropy gas, so the coolest gas that would, if left undisturbed, would go on and form stars. They drag this gas out of the center of the galaxy. So this is a cartoon, but now I will show you data where we can see all this. So what you can see here is a pressure map of the same galaxy M87 for which I showed you the jet at the beginning. So how did I create this pressure map? I got the Chandra data from the Chandra satellite, very deep data, more than a week-long observation of M87 with Chandra. And because M87 is bright, there are many photons, I could actually take the image and divide it into 16,000 different regions. And for each of these 16,000 regions, I could fit a spectrum. And from each of these spectrum, I could determine the temperature and the density of the gas. And as you know, temperature times density is pressure. So this is how I created this pressure map. What is overplotted here are the contours of the radio emission. And if you look at this pressure map, you can see that it's like if you throw a stone into a pond, you can see one of these rings here and another one here. These are the shock waves that are propagating from the center of the galaxy, from the central supermassive black hole. Now, if we zoom into this region, then we get this. You can see here the jet in X-rays. Again, here you can see the contours of radio emission, and you can see that here where the radio emission is strong, there is a deficit in pressure. There is a deficit in pressure because this radio emitting plasma provides some of the pressure support there. So the thermal pressure of the X-ray emitting gas is missing there. And so these are actually the bubbles of the relativistic plasma. And as these bubbles initially expanded supersonically, they were driving this shock wave, which you can see here. So this sudden change of pressure, this is a shock wave that is propagating from the center out. Here is another bubble, another cavity. This one already detached from the jet and is rising this way buoyantly. So these shock waves are one way how the black hole keeps heating the gas. It sends out one of these shock waves every 10 million years or so, and these shocks, as they are passing through the gas, they are heating it. Now, the temperature and density can also be calculated, converted, using them we can also calculate and determine the entropy. So you see that this is the entropy map made of the same data. Here you cannot see the shocks anymore. Here you can see this kind of low entropy outflows. These outflows, the fact that the entropy is low in these outflows means that the gas is coming from the center. If you have a system in equilibrium, then the entropy is the lowest in the center, and then radially the entropy keeps rising. This is, in that case, the system will be in convective equilibrium. Now, the system is not in equilibrium because there are these outflows, and the fact that the entropy here is similar to the entropy here means that the gas here came from the center. So, some previous outbursts, in some previous outbursts, we think that the bubbles of relativistic plasma direct this gas out from the center of the galaxy. Back in 2010, I calculated that actually these outflows contain as much, almost 1 billion solar masses of gas. 1 billion solar masses of gas, which if left undisturbed in the center of the galaxy would go on forming stars. So actually in M87 we see this kind of black hole feedback in action, preventing star formation. Yes?
Yeah, so I want to see if I understand this. It's fascinating. The jets go out, blow up these bubbles. We see the lack of them in the X-ray light, because the X-ray light, we're looking at the diffuse hot gas. And so we have these bubbles blown out of this relativistic jet coming from a black hole feeding, I guess. And then you're saying here that by doing your entropy map, which I had not seen this kind of work before, but you're talking about it's dragging up probably many more times its mass of the jet, much more of that. I'm guessing here, but a lot of the mass that's coming from the center is actually cold material that is somehow connected to the...
I mean, it's still not cold, it's still an X-ray emitting gas, so it's still 5 to 10 million Kelvin hot.
Right. I didn't mean ISM cold, but colder than the rest of it, and that follows through in these...
Yeah, so in the wakes of these bubbles, you see it also in simulations, in the wakes of these bubbles are capable of uplifting huge amounts of gas from the center of the galaxy to cause these outflows.
Thank you.
So this is physics that, this is a kind of physics that we also know from the Earth. This is the unpronounceable volcano in Iceland, where when the hot air breaks through the lava, it expands supersonically initially, driving these blast waves through the surrounding medium, which you will see in a moment. Yeah, here was the blast wave. And then this hot gas is rising buoyantly through the atmosphere, dragging up the ashes from the center of the volcano. So you will see this again. Hot air breaking through the lava, expanding supersonically, causing these blast waves, and afterwards rising buoyantly, dragging up the ashes from the volcano, stopping the air traffic over Iceland. It's the same what we see here in M87, where the blast waves are these shock waves that we see in the pressure maps, and then the relativistic plasma rising buoyantly. This is the radio emission in red, dragging the white thing, which is the low entropy gas, up from the center of M87. And if you...
Same thing happens in an atomic bomb.
Yes, exactly.
It's the same
I just prefer to talk about volcanoes instead of atomic bombs. And if you think that this is extreme, this is by no means extreme. This is another galaxy cluster at higher redshift, and this one, this is again a composite image. Here you see the optical galaxies, here you can see the intergalactic medium in this blue, and then in pink you can see the radio emitting plasma. And you can see that here this bubble is 200 kiloparsec large. Actually, I might have made here a mistake. I think this was 600 kiloparsec. Huge. So if you think about this, this is really fascinating, because you have a huge galaxy cluster in the center of which you have a black hole, the size of which is smaller than the size of our solar system. And something as tiny as this black hole, that is smaller than our solar system, is controlling the evolution of a whole galaxy cluster. This is as if you had a blueberry on the Earth controlling the whole physics and evolution of the Earth. I think this is really, really mind-blowing. And because these outbursts happen repeatedly, I call them the beating hearts in the centers of these galaxies. Now, I showed you that these black holes, they offset the cooling of the gas. They balance, with their activity, they balance the cooling of the gas. Now, they do it very well. They balance the cooling maybe to 90-95%. But some cooling occurs in these systems. We know it from X-ray spectroscopy, where we very recently, actually, just last summer, detected cooling lines of oxygen 7 in the centers of some of these systems, which indicate that some of this gas actually does cool below 5 million Kelvin. Also, when we look at many of these giant elliptical galaxies that are otherwise red and dead, they have these spectacular H-alpha filamentary structures around them. Now, the H-alpha emission is emitted by gas that has a temperature of 10,000 Kelvin. So you can see that there is some colder gas, there is some cooling going on. And I was actually curious whether there is even colder gas, 100 Kelvin gas. Many of these giant elliptical galaxies have been observed with radio telescopes to look for neutral hydrogen, and no neutral hydrogen has been found. They were looked at to see molecular CO emission, but no CO emission has been found. But it turns out that there is the atom C+, which the cooling lines of C2 can be very, very strong, can be more than a few thousand times stronger than CO. So I looked at some of these giant elliptical galaxies with the Herschel satellite, which is capable to look at this C2 line emission. And we detected booming C2 lines in many of these otherwise red and dead giant elliptical galaxies. So some cold gas is present there. And we could map also its distribution. So what we found is that this C2 emitting gas is following the H-alpha filaments really, really nicely. These contours are the H-alpha contours, which I showed you before. And then the colors show the intensity of the C2 emitting gas that we were mapping using the Herschel satellite. And the nice thing about detecting the C2 emission with Herschel, that we could also map its velocity distribution. So here we can see the velocities, and it turns out that the velocities of the C2 emitting gas are the same as the velocities of the H-alpha emitting gas. H-alpha, as I said, 10,000 Kelvin, C2 100 Kelvin. And then there are some observations in infrared by other people which detect 1,000 Kelvin gas, and it turns out that they have again the same velocities. So what we have here is a multi-phase medium of cooling and perhaps also mixing. In some of these systems, actually, this gas forms these rotating disks that you can see here, which is very nice. In the others, you don't see this rotation. And we could also look at the velocity dispersion of this gas, and it's several hundred kilometers per second, which means that you cannot have such velocities in one gas cloud. This is not one gas cloud. What we have here is many, many cloudlets that are somehow orbiting, following perhaps the motions of this hot medium and orbiting, moving chaotically within the galaxy. So this cold gas is made of many, many tiny cloudlets with a very small volume filling fraction. So there is some cold gas in these systems. Now, I was curious, how does it relate to the hot X-ray emitting atmospheres of these systems? So what I did, I took data from the Chandra satellite, and I basically divided the data assuming that the emission comes from spherical atmosphere. So I determined the temperatures and densities in spherical shells for these galaxies based on Chandra data. And from the temperatures and densities, one can calculate the entropy of the gas. And what I found was that the systems which don't have any cold gas have entropy distributions like this, while those systems which have cold gas have lower entropies, which immediately showed me, wow, there is some connection between this cold gas and the hot gas. So this cold gas must actually come from cooling. There is some cooling maybe occurring in these systems. And there were theoretical papers published in the past 3-4 years which showed that there is some kind of a threshold in these galaxies where the cooling time is less than 10 times the free fall time within that galaxy. Somehow thermal instabilities will occur. Now, why is it exactly 10? When I'm at conferences, people keep still fighting about why is it 10, but it's 10, it comes out of their simulations. That when it's less than 10, thermal instabilities will occur in the atmospheres of these galaxies. So, and here are my data now. These are the cooling time over freefall time for systems which have no cold gas in them. We don't see any H-alpha filaments, we don't see any C2 emission. And you can see that in this ratio is more than 10 in all of these, except this one system that I will come back to. And all the galaxies that have cold gas in them, this ratio goes below 10. So this proves that, or this indicates that indeed the cold gas in this system occurs from thermally unstable cooling from the hot X-ray emitting atmospheres. So now what about this guy? It's more than 10 everywhere except the very, very center where it really, really drops down. This is this galaxy, NGC 4261. Now the X-ray emitting atmosphere would be about this big in this system. And then there are these huge jets emanating, which indicates that as the atmosphere thermally unstably cools in the center, it feeds the supermassive black hole, causing these huge jets that then punctuate through the atmosphere of the galaxy and deposit the energy outside of the atmosphere of this galaxy, which extends only about this much.
Excuse me, what do you mean feeding the black hole?
So this is the material that falls into the supermassive black hole, and as it is falling, it forms a jet it forms an accretion disk from which then these jets are launched. So, but we find also something really counterintuitive. Systems, just based on the energy deposit in these lobes, what we calculate, the systems that are cold gas poor have larger jet powers than the systems that are cold gas rich. This is kind of mysterious. We have systems like this one, NGC 1399, which has no cold gas. It has a very spherically symmetric, nice X-ray emitting atmosphere, and it has these huge jets that has a large power. And then you have a system like NGC 5044, which has these huge H-alpha emitting filaments, here now shown in red, so lots of cold gas, many X-ray cavities, its X-ray morphology is very disturbed, indicating that the black hole is interacting with the surrounding medium, but the jet power is tiny. I mean, this is this is the radio image. Is this tiny thing here in the middle, tiny radio jet. So what's going on? Do we see here a cycle, a feedback cycle, or is this an end state? We don't know. And in order to study this further, we need to study this feedback using many telescopes at many different wavelengths. With Chandra, we study the X-ray emitting gas, in radio, jets, optical UV, any star formation that might still happen at very small levels in these systems. And now we don't have Herschel anymore, but the capabilities of Herschel, Sophia has the capabilities of Herschel. So I actually in 2 weeks will fly on this plane to look for cold gas, C2 emitting gas in some of these giant elliptical galaxies. And then with ALMA, we will be able to follow the cold gas all the way to the black holes, so to see how this cold gas is feeding the black holes, or it's not. Who knows? So we will keep working on this for the next years. Now, I started out by saying that we need to understand the physics, microphysics of this intergalactic medium. What is its viscosity, conductivity, and one way of learning about it is actually studying so-called cold fronts in the atmospheres of galaxy clusters. Now, you might have heard about cold fronts in the atmosphere of the Earth, but there are also cold fronts in the atmospheres of galaxy clusters. So on this image here, you can see a cold front in the Earth's atmosphere. What is a cold front? It's nothing else, just you have a mass of cooler air that moves through a mass of hotter air, as you can see here. And as the cooler air moves through the mass of hotter air, it is uplifting it and creating turbulent thunderstorms or dust storms, as in this case you can see here this dust storm that delineates the cold front. We can see the same thing in galaxy clusters when you have cooler gas moving through a hotter gas. For example, in a merger, when you have a galaxy cluster that is cooler and it collides with a hotter galaxy cluster, you have a merger, then you might see a cold front as the cooler intergalactic medium is moving through a hotter intergalactic medium. Now, how this edge will look like depends now on the viscosity of the gas. If you have shearing motions along this edge, then you may create so-called Kelvin-Helmholtz instabilities, which are little turbulent eddies. So by seeing how turbulent this edge is, you can learn about the viscosity of the gas. Often, at this edge, you have a really strong temperature discontinuity. And by seeing how how narrow is this temperature discontinuity, you can learn about the conductivity of the gas, how the heat is conducted from one side to the other. So these systems allow us to learn about these microphysical properties of the intergalactic plasma. So I studied such a cold front again in the Virgo cluster, which is M87 is in the Virgo cluster. Here is actually M87 in the center, and this cold front is here 100 kiloparsec north of M87. Now, this cold front is not due to a merger, it's simply due to so-called gas sloshing. It's, you can think about it when you drink wine. Imagine that the glass is the gravitational potential of the galaxy cluster, and the wine in the glass is the intergalactic medium. If you have a merger, then you disturb the gravitational potential. You move it a little bit around. When you move the wine glass a little bit around, the wine will start sloshing in the glass like that. The same happens with the intergalactic medium, which is sloshing around the center of the Virgo cluster. The low entropy gas, I showed you about the entropy distribution before, which sits in the center, gets sloshed around, and then you create these cold fronts, these discontinuities in temperature and surface brightness. So in order to study it, because this is the nearest cluster cold front in the sky, we can really have an exquisite resolution on it. I observed it with Chandra for about a week. So really, this is a really deep Chandra observation. I wanted to study how turbulent the edges are. But instead, when I looked at the data, I found these linear structures which nobody expected to see in this galaxy cluster. Nobody. And I was really, really surprised what they might be. We named them pitchforks. When we did some numerical simulations and when we included magnetic fields, it turned out that they arise naturally from the simulations once you include magnetic fields. I don't want to bore you with details how, but this just shows you these features don't appear if you don't include magnetic fields in your models. When you do magnetohydrodynamic simulations, once you include magnetic fields, these features will appear naturally. Yeah?
Dr. Werner, you mentioned that at these interfaces there can be Kelvin-Helmholtz instabilities, and those can be kind of like finger-like structures, and that would be at the boundary. And you're saying these were not the right scale for that, or?
No, they shouldn't look like this. They would be here. They would be here at the. This is inside the
boundary.
Yeah. And we know from the outer geometry that actually the sloshing is going in the plane of the sky. It's not along this direction, but it's along that direction, predominantly. So these are the surface brightness profiles along this feature, and we could actually show that the discontinuity is very narrow, only 2.5 kiloparsec. Now the mean free path of the electrons is 1.5 kiloparsec. Sorry, this is only 1.5 times the mean free path of the electrons. So this is very, very narrow. So actually any transport processes are suppressed across this interface, which again shows that there are magnetic fields along this interface. But there are also some other regions which are very, very disturbed. For example, this one. And they look like that the edge might here be broadened by Kelvin-Helmholtz instabilities, which we look at in projection. This is a simulated image how it would look like with the Kelvin-Helmholtz instabilities. Now I would like to zoom out a little bit from the centers of the galaxy clusters and show that actually black holes have an effect also on larger scales for the chemical enrichment of this intergalactic medium. Now what you can see here is a really, try to convince you, it's a really impressive image. This is the X-ray brightest cluster in the sky as imaged by the Japanese Suzaku satellite. The Japanese Suzaku satellite, it stopped working this summer. It was on a low Earth orbit, so it had a very small detector background and it was able to study very low surface brightness X-ray emission. So with this satellite, we mapped the Perseus cluster across 8 different directions. Now this is the field of view of the satellite, this small box. So we performed 85 observations with Suzaku to obtain this image. 85 observations which totaled more than 1 million seconds, which is more than 2 weeks, in order to map the Perseus cluster of galaxies. And then, among many other things, we were able to measure the metal abundances, the iron abundance in the intergalactic medium all the way out to the edge of the galaxy cluster. So how much iron is there in this intergalactic medium? What is its concentration? Now, why is this interesting? It's interesting to learn when was this intergalactic medium enriched. If it was enriched after the galaxy cluster formed as the galaxies are falling in, then we would expect metallicity distribution that is increasing towards the center of the galaxy cluster. It's because as the galaxies fall in and as their metal-rich gas gets stripped, this stripping, the efficiency of the stripping goes like density times velocity square. And as you are going inside in the galaxy cluster, the velocity of the infalling galaxy is increasing. But also the density of the intergalactic medium is increasing. So as you are approaching the center of the cluster, the stripping is becoming always more and more efficient. So this kind of enrichment by the stripping of the galaxies would cause a metallicity distribution that is increasing towards the center. Now, if you enriched the intergalactic medium before the galaxy cluster formed, they formed about 10 billion years ago, then you would have homogeneous, uniform iron distribution across the whole intergalactic medium. So for the first time, we were able to determine the metallicity of the Perseus cluster all the way out to its edge. And what we found was a flat metallicity distribution of about 1/3 solar. We were able to determine the metallicity in 78 different regions in all these different directions, and we found that it was basically everywhere the same. It was a very uniformly distributed iron abundance distribution. And actually, very recently, for the Virgo cluster, we were also able to measure the ratios of silicon, sulfur, and magnesium over iron, and you can see it's very, very close to the solar ratio. So the abundance ratios, the enrichment, is very similar to the composition of the sun. So in order to have a uniform iron abundance distribution, the galaxies 10 to 12 billion years ago, before the cluster formed, had to be very efficient in blowing out metal-rich gas. So what we proposed that in the period when all these galaxies formed, when there was a huge star formation rate and many supernovae exploded in the same time, and also the black holes were growing the fastest, accreting lots of matter, producing winds and jets. In this time, these galactic winds were able to blow lots of metal-rich material out into the intergalactic medium and then mix it there very efficiently. Because after the cluster formed, the mixing cannot be very efficient. I showed you that the entropy distribution is stratified. So the atmosphere of the cluster is convectively stable. It's very hard to mix the material across a megaparsec scale once you have an established entropy distribution. So before you had that, you had to put, the metals had to be put into the intergalactic medium before this stratified entropy distribution was established. So the conclusion here is that the combined energy of the accreting supermassive black holes and many exploding supernovae in the same time were the spoon that mixed early on the metals in the intergalactic medium, producing this nice latte that you can see here in the image. And I would like to end my talk telling you a little bit about the next big X-ray space observatory, AstroLABE. This is a Japanese-led mission with contribution both from the United States and from Europe. And the satellite, it will be launched at the beginning of the next year, will provide a factor of 30 improvement in spectral resolution. Now, whenever in astrophysics or anywhere in science you get a factor of 30 improvement in your observing capabilities, you can expect new, really exciting discoveries. I'm in the science team of AstroAge, and I'm working on the observing strategy for the primary galaxy cluster target, the Perseus cluster, which is the brightest cluster in the sky. Here you can see an X-ray image, and this is a corresponding optical image. When you look at the X-ray image, you can see that there is a lots of dynamical activity going on. Here are these bubbles, these ripples. There's a lots of dynamical activity, but so far we were unable to measure it directly. Because
the same scale?
Yes, exactly the same scale. We were unable to measure it directly because we didn't have the spectral resolution to measure any gas motions. Now, what we will do in the first year of the mission, we will perform these 11 observations. These are the fields of view for each of these 11 different observations. And for each of these fields, we will obtain a really beautiful high-resolution spectrum like this. The strongest line in the spectrum is the iron line. And from the broadening of this line, we will be able to determine any velocity dispersions. What is the turbulent? What are the gas motions? Currently, we have no idea whether the gas motions are 100 kilometers per second, 500 kilometers per second. We really don't have any idea currently. And from how this turbulence works, how it dissipates, we again can learn about the viscosity of the gas. So what we will be able to do here, if you have a turbulent eddy like this and you point here, you will see predominantly coherent gas motions. So you will see line shifts. If you point to a place like this, you will see line broadening. So we will be able to study the structure of gas motions in the Perseus cluster. We will be able to measure, to study the structure of turbulence and measure how the black hole-driven gas motions are driven, how they dissipate into heat. We will be able to measure the multi-temperature structure of the gas, how it cools. So this will be really exciting. And in M87, I showed you these outflows. We will be able to measure the velocities of these outflows. So how the black hole, how fast the black hole outflows are actually propagating through the intergalactic medium. And we will be able to measure the abundances of many chemical elements produced by the supernovae that exploded within the galaxy clusters. So this will be really exciting. This will be next year, but the next decade in discovery will be even greater. We will have the James Webb Space Telescope, 30-meter class telescope. We already have ALMA, which is really amazing. And because I mostly observe in the X-ray band, I'm really looking forward to the Athena X-ray Observatory, which is the next big European X-ray space observatory that will be much better than anything that we had before. Thank you for your attention. And please,
We have time
Please ask me
for some questions.
Do you only see jets coming from the CD galaxy in the clusters? Do you ever see any of the smaller components contributing to the jet outflows?
For example, if you look at the Virgo cluster, you see jets not only from M87, which is the sitting in the center of the Virgo cluster. There are also other giant elliptical galaxies like M84, M89. They also have their own small X-ray halos centered around these galaxies. So they have their own small cooling flows that might be feeding the jets in these systems. So we see jets in also in these different giant elliptical galaxies within one galaxy cluster. But of course, the jets are always the most prominent in the central cluster galaxy, which has the strongest cooling flow around it.
I must say, I'm going to follow up because my mind went in very similar lines. I think with your enrichment, are you saying the dominant source of enrichment throughout a cluster is still the CD, even though your evidence is saying it's in very early times? I guess I'm saying, what is the time evolution of the sort of difference in hierarchy of having a massive centrally dominant galaxy versus the other galaxies? Obviously, that's accreting these other galaxies over time and becoming larger and larger. So I was wondering, can I think of it as a democratic process that multiple cores and intermediate and supermassive black holes are enriching the whole cluster environment at early times?
So what I forgot to say that this is true outside of the very center of the cluster, that the metals are distributed uniformly. The metals distribution peaks always at the central cluster galaxy. So that's where there is always this metallicity peak at the central cluster galaxy. Because, for example, just the stellar winds and the Type 1a supernovae, which exploded in the central cluster galaxy within the lifetime of the cluster already, are capable to build up a metallicity peak. So what we did in that analysis, we excluded this peak around the central cluster galaxy and looked at the outskirts. How is the metallicity distributed in the outskirts? Now, I told you about this stratified entropy distribution. As the galaxy cluster grows in mass and the X-ray emitting gas is hot because of the shocks as it actually falls onto the galaxy cluster. It's heated by the shock heating as it falls into this huge gravitational potential. Now, as the galaxy cluster grows, these shocks are becoming stronger and stronger, so the entropy is rising as you are going outwards. The fact that out there we still have a flat metallicity distribution means that the intergalactic medium, everything that is falling onto the cluster, has to be enriched to 0.3 solar, because you cannot, once this entropy distribution is established, you cannot mix efficiently radially. So that's why we concluded that the intergalactic medium had to be enriched before the cluster formation. Which also means that the intergalactic medium in the filaments, which we cannot yet observe in X-rays because their density is low, which connect these, to these massive galaxy clusters, and that the intergalactic medium in these filaments is probably also enriched to about 0.3 solar.
Mine's like a clarification question about the Schloss gene with the wine.
Yeah.
What did you say was the cause of that?
The
Is it
cause
the
of-
medium, or is it energy?
I'm sorry, I went very, very fast over that. So, in our model, when we try to model the sloshing in the Virgo cluster, then what we get that about 1.7 billion years ago, there was another subcluster that moved by very close to the center of the cluster, about 1.7 billion years ago. Another subcluster, a smaller system, group or huge giant elliptical galaxy, moved past the center of the Virgo cluster and it disturbed its gravitational potential. As its gravitational potential got disturbed, then it got moved a little bit, and then this low entropy gas tried to follow it, but there is ram pressure that is acting upon this gas. So then it slowed down, it decoupled from the center of the gravitational potential, and then it tried to fall back, and then it started moving around like that. So it's very similar to when you just move the wine glass and then the wine tries to follow it. Even when you stop moving it, it will still be sloshing around. So the sloshing can persist for billions of years.
Have you tried to model the Fermi bubbles?
I
Too small.
I didn't. So what are the Fermi bubbles? So you might ask that we see all these bubbles or huge radial lobes around these galaxies that I was showing you. What about our Milky Way? When you look at the center of our Milky Way galaxy, you see there a black hole that is not very active today. It is sleeping. It is not feeding very much. But relatively recently, it has been discovered that around our Milky Way galaxy there are these bubbles of gamma ray emission. Where are they coming from? And one of the hypotheses is that they might be coming from a previous black hole activity in the center of our galaxy, so that it used to be active from these bubbles, and right now it is just sleeping before it will become active again. This is one of the hypotheses, and there are many people who believe that it's due to that. And there is another theory that they might be due to a star formation episode in the center of our galaxy. These are the two models currently.
Well, one of your earlier slides was talking about hot gas heated from the jets. It was also talking about unstable cold matter. What is unstable cold matter and what makes it unstable?
So what I said that thermally unstable cooling, you have this 5 million, 10 million degree gas in these galaxies. And what I said that if the cooling time of this gas, because it cools just by emitting the X-ray photons, over free-fall time is less than 10, then there might be some so-called thermally unstable cooling. So you have one piece of the gas that starts cooling, and then it just goes from there, and then it will fall in, forming filaments of cold gas. And then this cold gas might actually be the material that then feeds onto the black hole and triggers the next outburst, which then again slows the cooling, stops the cooling. Then you again get this episode of cooling, triggers another black hole outburst, which then stops it again. That's why I'm talking about the beating hearts, because these are periodic events. Once cooling starts up the black hole, which stops it.
A follow-up on that was just a question about that beating heart, right? I've seen simulations like Phil Hopkins and the accretion of the black hole. You're seeing the other end of it, the blowouts, the gas that's going out there. What do you think the cadence of this is, of the beating heart of the black hole in the center of galaxies?
So when we look at some of these systems, what we see is about 10 to the 7 years. But I must say that actually some accretion goes on almost all the time. We have radio data for many of these nearest, brightest giant elliptical galaxies with X-ray halos. And in the center of each of them we see some radio, at least a point source, some radio emission, which indicates that the black hole is accreting on some level and is producing some jet activity. So at least these systems which have these X-ray atmospheres the black holes seem to be accreting all the time. Now the accretion rate can of course change, but some accretion happens practically all the time. Now, I was talking here about the so-called radio mode feedback, jetted feedback, where the black holes are accreting at not such a high rate, but they are producing strong jets. But there are also the radiatively efficient black holes, about which I didn't talk today, where we have really, really bright accretion disks that produce winds, but they don't produce jets. But this is for another talk.
We'll continue with some questions, but those of you who need to leave, let's thank our speaker again.